XianHui Ge from Shanghai University. His title is Hyperscaling Violating Black Hole Solutions and the Transport of a Quantum Critical Point. Could you please start?
Okay. Okay, first of all, I would like to thank all of the organizers for organizing this web workshop. It's the first time for me to talk on in the internet. So today, my talk is about hyperscaling violating black hole solution and the transport of quantum critical points. This work is done together with Yunsu Su, Zhang Jinxing, and Genho Song. They contribute more than 80% of this this work. So I only give some minor contributions. I mainly refer to the first reference in this talk. So the afterline of my talk is the following. Firstly, I will give some introduction and motivations. I think Yunsu already mentioned such direct material and non-direct material in his previous talks. I will first mention the experimental result about magnetic gap of manganese doped bismuth 2 tellurium-3 of this experiment, and how this experiment is related to the direct material and the non-direct material phenomena. Then I will switch to the holography, and as a warm-up exercise, I will first consider a hyperscaling violating black hole without magnetic impurity, and then I will consider impurity effect on the transport. Then we'll analyze the quantum transport and the z-theta space. And in the end, I will present the conclusion and outlook for the future work. So we know that the direct materials is such as graphene and topological insulator surface has a direct cone. So we call such material as direct material. The reason why direct material can relate to holography is because that the transport anomaly in graphene demonstrate that a system known to be weakly interacting may become strongly correlated if the Fermi surface is small enough. For example, for the effective coupling in a system with a direct cone, this alpha effective can be larger than 1. So this means the Coulomb potential in this case is not so strong. So the fundamental reason for the appearance of the strong interaction in graphene is the smallness of the Fermi sea. And also for the surface states of topological insulators, there are some very rich physical phenomena. For example, there is a weak anti-localization, quantized anomalous Hall effect, Majorana formula, and topological magnetoelectric effect. So we can see in this this finger, as the doping increase, the Fermi surface becomes smaller and smaller. So when the Fermi surface is touched the Fermi energy in this area, this red line, and then it can be described by using strong coupling system. And also this finger is from experimental data. So we can see clearly there is a Dirac cone here. Last year, there is a experiment about the magnetic gap of Managas doped bismuth to tellurium 3. They found that for this material at the topological surface states at 20 Kelvin. This finger is about 20 Kelvin. The first surface states become split into two. We can see that this blue line should, this red line is 20 Kelvin magnetic doped material, and this blue line is 1 Kelvin doped. We can see that it's split into two lines. So, so there is a gap there. So this gap is original from magnetic impurity. The reason is because that for this material, the ferromagnetic phase transition is TC is 10 Kelvin. So below 10 Kelvin, at 1 Kelvin, there are two equally intense components here. And also the magnetic origin of this gap can be seen from the RPS data. We can see that at 6.5 Kelvin, the spectrum at the Dirac point is clearly spin polarized. So we can see here the magnetization for different bending energy is from here is M plus and here is M minus, and also there is a gap at 6.5 Kelvin. So so this means that if we consider this as some Dirac or non-Dirac material, we need to consider magnetic impurity if we want to describe it holography. So we need to consider the magnetic impurity. So that's the experimental result gave some hints about what we shall include on the holograph side. And also, we know that a quantum critical point is characterized by Z and theta from the dispersion relation omega proportional to Kz and entropy scaling like this. So the corresponding black hole metric use the same scaling and symmetry as follows. So we have d s squared goes like this. So so here let's try to explain why we consider half scaling violation for Dirac material with Z equal to 1 and theta equal to 0. In the previous paper by Yuan Shou and Sandin and Guillaume's paper, they already found that for direct material with Z equal to 1 and theta equal to 0, this graining with the current data of surface of topological insulators. However, in this figure, we can see that the direct point is not so clear in this figure. Maybe there is some deviation from direct point. Later we can see that for Z equal to 1.5 and Z equal to 1, agreeing with the experiment data well. So that's why we consider this hyperscaling validation. And for non-direct material, it means that you don't have a direct point. So then you have such hyperscaling. Then we claim this is non-direct material. As the surface of topological insulator is doped with the magnetic impurities, the Fermi surface becomes smaller and the surface gap is open, as shown in this figure. So Dirac cone disappears, and the system is strongly interacting when the surface band touches the Fermi level. So the qualitative difference of transport closely depend on the dynamical exponents of quantum critical point via various the Z and the theta. So that's the reason why we consider transport coefficient with hyperscaling violation and magnetic impurity from holography. And also we focus on the consequence of Dirac cone and the surface gap of topological insulator. We do not focus on the reason of the Dirac cone and the surface states of topological insulator. That's that's our annotation for the following study. So that's the motivation why we consider hyperscaling violation black hole system. Then we write down the action. So the model is considered as the following. Here the first Lagrangian zero is here we have a rich scalar, and this term is the potential term, and we have dilaton, and also we have a gauge field, 2 gauge fields, and the last term here is used to break translational symmetry, and this interacting term plays the role of magnetic impurity. So this model have a black-green solution as follows. We have 2 gauge field. The first one is auxiliary gauge field, which makes the metric which is ellipsis metric. The second gauge field is a real maximum field, which makes the black hole charged. So, and also we have chi I1 and chi I2 linear actions. So here we can see that the Lacan function Fr goes like this, and the last 2 terms correspond to magnetic impurity terms. So as Z goes to 1 and theta goes to 0, we can recover the result given by this paper more than 2 years ago. So this means that Z equals to 1 and theta goes to 0, we can recover the Dirac cone result. So that's the black hole solutions. And as a warm-up exercise, let's consider a black hole solution without the impurity, magnetic impurity. This means we neglect this. We just delete this term and see what happens there. In this case, there are 2 branches of black hole solution. The first branch is goes like this. We can see that here the Q2 and B are integral constants. So if we switch this Q2 and B, switch each other, we can obtain the second branch of the black hole solutions. So here the Q2 is a charge and B is a magnetic field. And also for the first branch, we can have the Hawking temperature goes like this. So this is a charge term. This is magnetic field. This term is related to the linear actions. And also for the second branch, we can also write down the Hawking temperature.
Sorry, can I make a question? I don't understand why these 2 solutions are actually different. It looks to me you are just recalling 2 parameters in a different way, but it's exactly the same solution.
They have different meanings, in fact. It depends, you choose a different integral constant. Later, we can see that they will result in different transport behavior.
Okay, I see.
This two, yeah, they will result in different,
Thank you.
Conductivity and magnetic conductivity. Yeah. We can see later. Yeah. So we can calculate the magnetothermoelectric DC conductivities. The Lipschitz spacetime with 2 gauge fields. One is auxiliary field and one is gauge field. And the problem here is that the mixture of the 2 gauge fluctuation leads to 2 times 2 conductive metric with non-vanishing off-diagonal components. So here, to avoid ambiguity, we set the current induced by auxiliary gauge field to be vanishing, so that the reduced conducting metric is only related to the black hole charge. We can see that even in the absence of linear action, a finite DC conductivity can still be obtained for finite charge Q1 and Q2, even without momentum dissipation. Let's see. I just wrote down the conductivity. We just see that we set the momentum dissipation term to be vanishing. That means here the beta go to 0, just go to 0. And we can write down the thermoelectric conductivity. Isometric goes like this. For simplicity, let's just we choose the magnetic field to be 0, then the electric conductivity reduced to a very simple form like this. Here the Z1 and the Z2 are couplings related to the dilaton fields. So for this expression, if we want obtain the linear resistivity, we can see that it corresponds to theta equal to 8/5 and Z equal to 6/5 for the first branch of solution, and theta equal to 0 and Z equal to 2 for the second branch of the solution. Without momentum dissipation. Because the two charge can, these two charge can interact with each other. So the linear in temperature resistivity can be obtained even without the momentum dissipation. And also we can plot the next single as a function of magnetic field and temperature. So this first row is correspond to theta equal to -1 and Z equal to 1 for the second branch of the solution. And we can see this for different temperatures, the next single behave differently. But as the next single as a function of the temperature, we can see that this next single goes up with as the temperature increase. This means that this behavior is not the incoherent metal behavior. This behavior is conventional metal behavior, right? And also for zeta equal to for the without a momentum dissipation case, we can also plot the next single as a function of magnetic field and temperature. So yeah, for these two cases, the next single decrease as the temperature increase. So this may explain why we call these two black hole solutions different branch of black hole solutions. Okay. So let's go back to the impurity. Go back to the to add the magnetic impurities into the black hole solution. We can classify Cation of the Z theta space. Yeah. So first of all, let's write down the entropy density and the Hawking temperature like this, and we can plot the. We can see that the Hawking temperature has many terms. Here is this neutral contribution, and here the magnetic and charge, and also this is the magnetic contributions. We have 4 terms here. If we plot the Hawking temperature as a function of horizon radius, we can see that there are 4 different behaviors. We can divide it the whole zeta and theta space as the following. In the region I, here it corresponds to this line. This means it can, the Hawking temperature can be negative in this space region. And also for the O region, we can see that the Hawking temperature is always negative. This means these two space region is not very physical, right? And for the second region, we have we have a minimal temperature here. From here, we can see that maybe there is a Hawking phase transition because for a given temperature, we have two horizon radiance, small black hole and a large black hole radius. The same for the fourth region. So, but in this talk, I'm not going to talk about Hawking phase transitions. For the red line, we can see this line is always positive. So this is very healthy. We can utilize this to study our transport behavior. And also the near horizon geometry of this black hole solution is ADS2 times S2. So we can study the transport with magnetic impurities. So we consider the linear response perturbations as the following. And we can obtain the transport coefficients, which is actually is a metric. Here, the sigma II is a longitudinal conductivity. Sigma ij is a transverse conductivity. Alpha II is a Seebeck coefficient. The kappa bar is the thermal conductivity. And then we can also obtain the resistivity metric, goes like this. And also we can read off the thermal conductivity and coefficient and nest singles. So because of as z go to 2 and theta go to 2, the metric function have singularities. So these two lines divide the whole space into 4 regions, A, B, C, D, and but these 4 regions are not each region is physical. So for the reality condition of the Q1 requires 2z minus 2 times 2z 2 plus z minus theta to be big or equal to 0. And also the now energy conditions 2 minus theta and 2z minus 2 minus theta to be big or equal to 0. We can plot the so the shadowed region is a physical region. Okay. So we can calculate the magnetic transfer and we can see that this region also we can see that there is a weak anti-localization and a weak localization phase transitions in this space. It depends on the sign of this longitudinal conductivity. For weak anti-localization, it corresponds a minus sign of h squared. For weak localization, it corresponds to positive sign of h squared. So So we can see in this here, the first finger is that if the magnetic impurity is 0, then most part of the validated regions is weak anti-localization regions. However, as the magnetic impurity increase, and we can see that the weak localization regime expand. Here is QK is 0.7, is QK 0.4. So finally, it can fill the whole region of C and D. I mean, the C, D is the baseline is limited by the non-energy condition. And also for different zeta and theta, we can plot the longitudinal connectivity as follows. So for QK is 0, QK 0.7. And also this is a corresponding Dirac-Cohn regime. And this here we choose Z to 2.2. So we can see that the longitudinal conductivity behaves very differently for different Z and theta. So, and also we can check the longitudinal thermal conductivity. We can also expand the thermal conductivity as function of small h. So, we can see that near z equal to 2, the sign of the coefficient is negative. Is positive. However, for transverse thermal conductivity, when the QK is 0, then this sign is determined by this factor 2 plus the minus 2 theta. Yeah, because yes. So now also we can plot the behavior of the thermal conductivity for different Z theta. We can see the behavior is very different. The most important, interesting thing is to compare the theoretical model with experimental data. Here we can see that we consider this conductivity different, defined like this, and we plot it as a function of the magnetic field. We compare the theoretical result with experimental data. Here we can see that this block is from experimental paper published in 2012. We can see that our theoretical model can fit with experiment data very good for ism over magnus is equal to 23.6. These two figures fit very well, very good. However, for this group fitting, they correspond to z equal to 1.5 and theta equal to 1. If we increase z, and we can see that the fitting is not so good compared to this experiment result. For example, if we choose, we fix z to be 1.5 and the theta is 0.9, there are some deviation. And also for this case, also there are some deviation. The best fit is the first finger. And also, for these two experimental fingers shown here, we can see that they do not fit very well. So that's our remarks. For this one, we can fit very good. But for this case, the ratio is 12.5 and the ratio is 10.3. These two are not very good. So maybe we need improve our model to fit both all these three experimental data. Here, let me give some conclusion. Yeah, we reported a new black hole solution with half scaling violation, which is relevant to magnetic impurity doped quantum material. And also finite conductivity and linear in temperature resistivity can be realized in the space-time without momentum dissipation. And also we calculate all transport coefficient and compare our model with experimental data. So we also studied the phase transition from weak localization to weak anti-localization as a critical exponent change. So in the future work, we want to study, for example, the superconducting dome for doped motor insulators. And also we want to look at the post-scaping for holography with hyperscaling violations. Here we show one fingers here. We can see that for different Z, this solid line is correspond to the hydrodynamics mode. The dotted lines is the post-scaping result. We can see that this post-scaping and the hydrodynamics, they fit very well in the small momentum regime. And also we can see that as theta changed, the solid line doesn't change very much. So this means this reflected maybe this post-scaping is not very sensitive to theta. It's more sensitive to Z. So we will study more carefully on this post-scaping phenomena with half-scaling violation. And that's what we are still working on. So that's all my talk. Thank you very much. So we have lot of time to discuss.
All right, thank you very much for your nice exposition. Now we have time for questions.
Hi, XianHui. Can you explain why do you introduce two gauge fields? Is it possible to find a Lifshitz violating solution with a single gauge field?
If you want to have a Lifshitz, even without the half scaling, even without half scaling, if you want to have such Lifshitz black brain solution, you need have two gauge fields.
So is there any theorem for that, or it's just I mean, by experience?
As far as I know, I don't know any theorem about. Previously, there's some work on realize the Galileo holography, but it turned out to be there's some problem there. So later, the people introduced two gauge fields. I think this is a very standard method to obtain the Lifshitz black brain by introduce two gauge fields. With only one gauge field is very difficult to, because you want to have because Lifshitz scaling is different from the ADS, because you destroy the previous the time and the coordinate is not equal anymore. So you need more terms to guarantee what if you want Lifshitz scaling, then there are no other physical unphysical result. So usually we introduce two gauge fields.
So I'm not quite familiar. So in higher dimension, for example, 5-dimensional case, you will introduce three gauge fields, or
I see. If you have for higher dimension, also still you two gauge field is enough.
Okay. And what's your interpretation, physical interpretation for A1?
For A1 is it's just to make your equation measuring more consistent, and also in this ground we just consider A1 is just make space-time is Lifshitz. But if we consider the fluctuation in this background, we can see that the perturbation of A1 contributes to the conductivity impact, because this, although it's auxiliary gauge field, but when you perturbate it is still we can show some conductivity. And yes.
Excuse me, I have a comment about Ian Liu's question. So as far as I know, you can have hyperscaling violating and Lifshitz solution using one U1 gauge field. This work has been done by Elias and Blaise, their paper.
Yeah, I also thought so. So then the question is,
the paper in 2006. Elias paper?
Not just the standard EMD theory, the Einstein-Maxwell-Dilton theory, just one U1 get field, you can have a hyperscaling violation solution.
This paper is which year of this paper is 2006?
Very old paper. Yeah, it's very long paper. So. Yeah, if you want, I can send you the archive number.
Okay, thank you.
Can I make one comment on it?
Yeah.
Right. So for the purpose of the hyperscaling violating geometry, as Lily said, just one gauge field is enough. But the problem is that, I mean, the Q1 in this theory is fixed, right? Q1 squared is given by G and theta, and it cannot. There are many problems for using the first gauge field as I mean the gauge field which is controlling the transport. So one has to introduce a second gauge field if you want to discuss the electromagnetic transport. So first gauge field is just supporting geometry, and the second gauge field is just controlling the transport.
So yeah, that might be true, but if you consider the UV is standard ADS, so you still have degree freedom to tune the charge density, correct?
Sorry?
Here you consider the UV is also hyperscaling violation. So I mean, within one U1 gauge field, so we consider the UV is ADS and the II is hyperscaling violation. So in this setup, you are still possible to tune the charge density.
So what carries the charge density, free charge density? Which field carries?
Yeah, you can still change, because the charge density is in the UV defined in the ADS boundary. The II is hyperscaling violation at the low temperatures.
Hyperscaling geometry into the big giant ADS, right?
Yeah, I mean in the IR, in the black hole, near the black hole horizon is hyperscaling, but in the UV, in the black hole boundary is ADS. In this kind of setup,
yes,
you have freedom to tune the charge density.
So now I'm asking, which field is carrying the charge density? You need to introduce anyway, you need to introduce other gauge field anyway, right?
Why?
Because charge density, in order to discuss the charge density, you need to, I guess, you need to introduce the gauge field anyway, because the Q1, as I said, Q1 is fixed in terms of G and theta. So Q1 cannot be the charge density. Right. So only when you have another Q2 that can play the role of the charge density.
I mean, when you heat up the system, so if the temperature is high enough, so you have a black hole solution that is not seems like hyperscaling, but as you lower the temperature to the very low temperature, the near horizon geometry is hyperscaling violation.
Yes. Yeah,
that's my point. You can, in the story with only one U1 gauge field, you can construct the black hole solution that is asymptotical ADS. And you have freedom to tune the charge density. And as you lower the temperature, so the near horizon geometry, it become more and more like hyperscaling violation. And the ground state is indeed the hyperscaling violation. And you said the charge density is totally fixed. That's my point.
By what?
Yeah, but by the
it's supposed to be free, right? We need to control it. So we need to be able to choose charge density freely. You cannot just fix it in terms of G and theta.
Yeah,
so in that sense, the first gauge field is a supporting geometry, not the gauge field dynamics. It's not a transport. It has nothing to do with transport.
That's in the two gauge field setup.
Right.
Yeah.
Yeah. My point is, if you use only one U1 gauge field, you can also construct. I mean, the black hole solution. I mean, in the UV, it's ADS. That's different from your setup here.
All right.
I mean, the UV
this solution is IR is a black solution, right?
Yeah, in this setup, the IR is ADS2, I think, and the UV is relation, so different setup. So my case is you can construct the story. I mean, the UV is standard ADS4. I mean, in the 4 dimension, and in the IR, I mean, the low temperature geometry is hyperscaling violating.
Excuse me, is that kind of thing is available any value of theta and z?
It's very general. It's very general, and yeah, you can construct this kind of solution. And this has been done by a lot of papers with Elias and his collaborators.
Yeah, I see. So what you're saying is that in that case, Q1 is not fixed in terms of the G and theta.
No, in the ground state, the IR geometry in the IR, it can be fixed like the story.
And so you are saying that in IR, Q1 is fixed, right?
Yeah.
Because that's in IR geometry is hyperscale violation. So then it means Q1 is fixed by Z and theta.
Yes.
But as go to UV, geometry is becomes ADS, right?
Yes.
Then Q1 becomes free?
No, it cannot.
So maybe we will check it.
I think there's a different story about it.
Yes. Anyway, thank you for comment.
Yes.
Yeah, I will send some paper to XianHui. Yeah, we will show some examples. Yeah.
Okay. Okay, thank you.
I'm sorry, I have another question related to this. So I don't understand the statement that the conductivity can be finite even without momentum dissipation. I mean, from the level of the symmetries, it cannot be.
Oh, yeah. You mean here, right?
Yeah, I mean, for example, at zero magnetic field, you are saying that the conductivity is finite even if you don't have momentum dissipation. But these are the level of the word identity and the symmetries. I don't understand how it can happen.
Yeah, this also for if we have two charges and this argument first provided by Julian Sumner, you know, in one of his papers, he claimed that the conductivity can be modulated by two charges. And because two charges have interactions. So
but with the interaction of the two, you don't have an interaction between the two gauge fields, right?
Because in the background action you don't have, but when you turn on the fluctuations, there is some mixture between these two gauge fields.
What is the physical?
You mean the physical origin of?
Yeah, of the final conductivity, because I can just imagine like a flow of two different charges moving, but why the flow should be stopped by what? I don't understand.
Matteo?
Yeah.
Matteo? So if you have the magnetic field, for example, then the conductivity is finite, right?
Yeah, but magnetic field breaks translations. So in the word identity appears on the right side, and that I understand.
You can see the formula that here for that purpose, the magnetic field and the Q1 field, the charge, are playing the same role. You look at the formula.
Yeah.
Well, I mean, Q1 is just like charge, but I don't.
Part of geometry, it's not a charge. So I think that we should not say present Q1 as a charge Q. We shouldn't use it as some charge Q1. It is just some number alpha.
But B breaks translation symmetry. Q1 doesn't. That's what I don't understand.
Matthew, I think we can first consider the case without the B. It also showed the case without the B. The conductivity is still finite. That's still confused.
You can see here for without B, we have sigma x Z2 plus this one, the second term.
So does it follow from the fact that you are setting the other? So how you compute this? You set one of the two current to 0, right? You set the current to the charge 1 to 0. Is that correct?
Yes.
And if you don't do that, what happens?
If I don't do that, they're too complicated. There's 4 times 4 components matrix. It's too complicated. So, yeah.
I see. Because it looks to me that here you are you have 2 charges moving, but then you are imposed that basically one set of charges is not moving. So the current is 0 basically. And is that the reason why somehow the other conductivity becomes finite? It seems like.
Yeah, it seems like this.
I see.
Because it's not very reasonable to choose Q1 to be 0, right? We can only choose
But apart from the simplification, what is the physical reason to put the other current to 0? Because the other current, I don't even understand what is the meaning at the boundary. What is the meaning at the boundary of the other current? Which kind of current it is? I mean, I don't know.
Yes.
Because for example, imagine a very simple system. You have like 2 kinds of charges. Let's call it, I don't know, red and blue, and they're moving in the middle of your system. And you want to compute the conductivity related only to, let's say, so you put an electric field, both currents will accelerate, and then you will have 2 kinds of currents, the current blue and the current red. And then you can compute basically the ratio between the current blue and the electric field and the current red and the electric field, right? But why you should put the other to 0? It looks to me like it's the same like in thermoelectric transport. When you compute the current, you don't have to put the thermal current to 0. You put the source to 0, but not the current.
Yeah, if we put the source to 0, then we don't have the background geometry will be cheap. So compared to, yeah.
No, I mean the source of the perturbation. So the background charge is fine, but then you don't want to put any source for the perturbations for that current, right? It's the same. Imagine you want to do thermoelectric transport. What you want to do is you want, for example, to remove a thermal gradient and put an electric field and compute transport. So here I would do something like the same. I wouldn't put any source for the charge Q1, and I will compute the current for the charge Q2. But that's not what you're doing.
Yeah, but for 2 current, for the first gauge field, we don't. What's the physical interpretation of the first gauge, the current? So.
Yeah.
So we have some discussion of on this. It's more reasonable to turn the current to be 0.
Anyway, I don't want to keep it too long. Maybe we can discuss it after offline.
Yeah. Okay.
It's a very good point that the A1 doesn't have any X dependence. So the question is a valid one.
Yeah, that's why I don't understand it basically. Because
you have a point.
I think it looks like it behaves like a magnetic field, but it's not a magnetic field. There's no translational break in there. So why it appears like down, like if it was a relaxation time? So for example, did you compute the word identities?
You mean word identity in this setup?
Yeah.
Not yet.
I see. Because maybe from there you can see what really matters. Because from the word identity you should understand immediately if you have a relaxation time or not.
Yeah.
Anyway, thank you so much. Yeah.
To my point,
okay,
so this result seems like a result from membrane paradigm. We know the story. Even for the translation invariant system, we can have a finite conductivity using membrane paradigm, but this conductivity is not the really conductivity from the boundary theory. From boundary theory, we have a divergent part plus this incoherent part. This part is finite. This part can be calculated from membrane paradigm.
Yes, but then if you do the numerics, you will see the 1 over omega pole in the imaginary part.
Yeah. If we do numerics, I mean, there is a standard technical, you will see the divergent, but from this, boundary horizon analysis using membrane paradigm, you will have a finite part, but not a divergent part.
And the membrane, yeah. Here, this is.
I think for systems, for systems with multiple currents, there's a possibility that we can define a combination of the current, just a linear transformation of the currents, such that the pole omega I, the coefficients, some combination in front of for these coefficients becomes 0, such that the conductivity is finite.
Yeah, that's the incoherent conductivity. Yeah, I mentioned. Yeah. Sometimes they call it incoherent part.
I'm not sure if
right. I wonder if.
This is a phenomenon for systems with multiple currents. It's not necessary to be related to translational invariance breaking.
No, but it's the same that Lee is saying. So basically, when you have two currents, each one overlap with momentum, but you can always do the combination that does not overlap with momentum, which is what Lee says is usually called the incoherent conductivity. So it's not sensitive to the momentum breaking or anything. So I wonder if with this boundary condition that you put here, like this J1 to 0 or whatever, you are actually implementing exactly what Jan is saying. This combination that does not overlap with momentum and therefore it's finite, even without momentum dissipation.
Yeah, I agree. I guess so.
Yeah, so as Matteo suggested, if you calculate the optical conductivity, can you see the pole, at 0 frequency?
You mean optical conductivity? Yeah. Yes, we can try to calculate. It's a good point to study. Already, because you have two current and you have this as too complicated. You have 4 times 4 conductivity metric, and so here we present the DC conductivity. For optical, we can maybe more clearly we can see whether there's a the divergence term or not. Yeah. And this result have been also have been obtained by other colleagues. Yeah. For this. I think the problem is the boundary condition. How to choose a more physical boundary conditions.
I see. Okay.
Okay, thank you for your comment.
Yeah. So can you say something about the localization? So I know you mentioned the localization
session, and then maybe we can continue until maybe 5 o'clock, where new talk begins. Matteo is a big and talk.